Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on December 10th, 2025, about 6 days ago. It shows that sparse autoencoder embeddings can uncover bigger differences between datasets than large language model annotators, at around 2 to 8 times lower cost, while staying interpretable and controllable. The paper is titled Interpretable Embeddings with Sparse Autoencoders, a Data Analysis Toolkit. And as we dig in later, the implications for how researchers explore massive text corpora and audit model behavior are pretty significant. Alright, Figure 1 lays out how the whole toolkit operates end-to-end. The left side shows a document passing through a reader large language model, which produces hidden activations for each token that a sparse autoencoder then turns into interpretable features like nouns or technical terms. The central bar marked verses represents max pooled activations across all tokens, so each document becomes a single concept-based vector. The right side lists what this enables in practice: dataset diffing, correlation discovery, controllable clustering, and property-focused retrieval. So Table 1 gives concrete examples of what those sparse autoencoder concepts look like in practice. The left half lists tone changes, where casual tone maps to a latent about casual or cool slang, and organized tone maps to question and answer transition points in educational content. The right half covers movie genres, where action, romance, and musical genres align with latents about action plot developments, will they or will not they tropes, and creative scenario building. Well, Figure 2 shows how strong the discovered differences actually are once a judge verifies them. Across all 6 comparison settings, the orange sparse autoencoder bars reach clearly higher frequency gaps than the blue and green large language model baselines, often by a wide margin. This means each sparse autoencoder hypothesis more reliably pinpoints a property where models or prompts truly diverge. In practice, that reliability matters because analysts can focus on fewer, sharper hypotheses instead of sifting through many weak or noisy ones. So, while Figure 2 showed that sparse autoencoder hypotheses were sharper, Figure 3 asks whether they can uncover subtle correlations that are actually planted in the data. The 4 scatter plots relate correlation strength on the vertical axis to semantic similarity of latent descriptions, and the colored points mark pairs tied to each synthetic pattern like Croatian plus emoticons or conservative academic style. The sparse autoencoder method highlights these points despite their low similarity, which means it flags genuinely surprising links. The table on the right contrasts this with a large language model judge, which only rediscovers each planted correlation in a fraction of random dataset shuffles, showing much less reliability. Alright, after those correlation results, Figure 5 compares how different embeddings cluster math solutions. The left block with dense embeddings mostly groups problems by topic, such as time or costs, because the cluster labels and examples all talk about the problem content. The middle block with instruction-tuned embeddings behaves similarly, just with more explicit step descriptions. The right block with sparse autoencoder embeddings instead highlights reasoning patterns, showing clusters about using transition words, giving detailed explanations, or doing direct sequential calculations. While Figure 6 compares retrieval quality across datasets using mean average precision, so higher dots mean better property-based search. The grouped points for prompts, responses, reasoning traces, the pile, biology abstracts, and short stories show that black and gray sparse autoencoder curves usually match or beat the colored dense baselines. The gap is especially strong on model-related corpora like prompts, responses, and reasoning traces, which most closely resemble the sparse autoencoder training data. The legend then confirms that combining sparse autoencoders with large language model re-ranking gives the top overall scores. Alright, while Figure 6 focused on retrieval performance, Figure 7 tracks how OpenAI models change across generations. The bar chart shows frequencies of behaviors like nuanced trade-off explanations, structured list layouts, and personalized follow-up advice, all rising sharply from GPT 3.5 to GPT 5. The final cluster of bars, tied to role plays, shows a big jump in personifying objects. The example panel on the right illustrates this, where responses become increasingly vivid and anthropomorphic as the model family advances. So stepping back, the key message is that sparse autoencoder embeddings turn opaque model activations into readable concepts, which makes dataset diffing, clustering, and retrieval both cheaper and easier to steer. More broadly, this suggests a data-centric path to auditing model behavior at scale. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.